So today we're going to kind of wrap up this whole big idea in terms of equilibrium and how you actually fit all these ideas into one kind of cohesive thought process. Then tomorrow we'll review. The test is going to be on Friday. Well, Big Mike, did you hear that?
Yeah, the test is on Friday.
So here's what you've got. If you look on your equation sheet, these are the three calculations that you have for delta G naught. Two of them we've talked about. Delta G naught, delta H minus T delta S, and then when we were in the electrochemistry unit, we used negative M, Faraday's constant, okay? So the one that we haven't really talked about is this one that's in the middle, okay? Which we'll get to. But we kind of have to work to get backwards to that point, and then that'll make sense. So an equation that is not on your sheet, but will form the basis of a whole bunch of different things, is this delta G equals delta G naught plus RT times natural log of Q. So this is where a whole bunch of kind of things that we've studied before are going to kind of begin to make sense in terms of this. So what's the only time you use something with a not value? When you're at standard conditions. 25 degrees Celsius, 1 atmosphere of pressure, molarities are 1. Okay? Standard conditions. So this is delta G, which is not delta G naught. Okay? So that delta G could be under non-standard conditions. Maybe it's 40 degrees Celsius. Maybe it's 15 degrees Celsius. Maybe the molarities are 0.5 as opposed to 1. Now, because of that, we're using Q instead of K. Because what's the only time you use K, as Nathan predicted, is when you're at equilibrium. So this is why this delta G is under non-standard conditions and why we're using Q instead of K. But this is where the magic happens. If you are at equilibrium, okay, if you are at equilibrium, delta G is going to equal 0, okay, because you're at equilibrium. That's an option. Delta G is going to equal 0. So then you've got delta G naught plus RT. Now, because we are at equilibrium, instead of Q, we're going to put K. Right? Okay? Go with this. Now, I want to get delta G by itself. Oh, okay. So I'm going to subtract that over, and then I'm going to get delta G naught is going to equal negative RT times the natural log of K. So this equation here comes from setting the non-standard conditions to equilibrium, and we resubstitute K in for Q. So when you would use this, okay, you would have to be told, hey, the system's at equilibrium, it's running at a certain temperature. Now, if you look at this in terms of units, which R value do you think you want to use? The chemistry R or the physics R?
8.314.
What units though?
I don't remember. I'm just going to
Atmospheres.
How about joules per mole Kelvin?
But isn't that what you use when you work with atmospheres?
That's liter atmospheres. So the reason that we want to use joules, and that's joules per mole Kelvin, is that way when I multiply it by Kelvin, the Kelvins cancel out, I get joules per mole. That's what Gibbs free energy is measured in. Okay? Seems reasonable. So let me go through a different version of this, but we're going to use gases instead, just nothing but gases. So we're going to look at this reaction into as a gas plus 3H2 as a gas. It's going to make 2NH3 as a gas. Okay? So this is the production of ammonia. So this is what's called the Arbor process. And the guy that actually facilitated this won the Nobel Prize in chemistry. But it was controversial because not only can you, this is a situation where it's good and evil. So this is ammonia used as a fertilizer.
Ooh.
Unfortunately, it's also used as ammonium nitrate as an explosive.
Yep.
So this created a controversy because they gave this guy the Nobel Peace Prize, but yet he developed a process that made large-scale dynamite and explosives happen.
Like a fertilizer. Like the
Exactly.
Oklahoma City bomb. Yeah.
Exactly. Now, so, but if you look at an equation that literally did change the world in terms of being able to feed people, this was a huge equation. So one of the things that allows us to grow a lot of food is synthetic fertilizers. Okay? So to give you some perspective on how like crop yields have changed. So when I grew up in Cheney, and there was a newspaper there called the Cheney Sun. Came out like once a week. And I remember this, I was probably in maybe second or third grade, because I remember like my parents talking about this story in the paper. And there's a wheat farmer out there, it's a big wheat country. And a wheat farmer grew a crop, and he made 35 bushels to the acre. Okay? Now, that made the front page of the Cheney Sentinel. Because prior to that, wheat yields were maybe, if you got lucky, maybe 20. Okay? So to make 35, that was literally newsworthy. Okay? But since that time, through genetics and through better crop science, now it's very common to see wheat yields of like 100 bushels to the acre. And so that's one of the reasons that allows us to have this is because of this reaction, the ability to produce ammonia. So that ammonia then gets put on crops grow much better, you get much higher yield. So this equation literally allows us to feed the world because of the fact that you're making ammonia, which is used in fertilizer. Yes.
Can you explain, like, so I'm at the golf course, right, and there's these little holes in the ground. Is that to get nitrogen? You know, they put the little holes in. And,
Like aerate the
aerate.
grass.
Yeah, that's
Nothing. Oh,
That's
nothing.
that's nothing to do with
Okay.
fertilizer.
Is the whole point
Now,
nitrogen to nitrogen ion?
huh?
Is it so that nitrogen is an ion, not the element?
Well, yeah, that take ammonia and turn that into ammonium nitrate, which is NH4NO3. That's another process. This is just the production of ammonia.
Is this the Haber-Bosch process?
Exactly.
We learned that in apes.
So
hey,
here's the point of this story.
That's how I remember.
At this point, you should be able to look at this reaction and tell me what you think the sign of delta S is going to be. What does that mean?
Negative. Michael, you really have a lot of words.
Why negative?
Going from 4 to 2.
Yeah. So I have 4 moles of gaseous reactant, but I only have 2 moles of product. So I got to figure my delta S is going to be a negative number. Okay? Now, right away, even though you don't know anything else, you haven't done any calculations, you haven't looked at any thermodynamic data, what's the possible sign of delta H? Could delta H be a positive number?
No,
It would never happen.
Why?
because that reaction is spontaneous. So
It would never be spontaneous.
So if I had a positive delta H
It's a cold and clean, and we don't like cold clean.
and a negative delta X, if that happened, this reaction would never take place. Okay? Because you're driving it away from enthalpy and entropy. Mother Nature's going, this is bad. This dog is not going to hunt. So right away, what's the only option that you could have for delta H? You'd have to have a negative delta H. Okay? You would have to have a negative delta H. That's the only way that it could work. So this is a classic example. You look at one equation, even without knowing the thermodynamic data, you can pretty much get an idea of what combination has to happen. All right. You have a negative delta H, which means it's what? Endothermic or exothermic? It's exothermic, so heat's going to be released. Okay. Now, so if you go through the math on this, I'm going to do this just to save some time. The delta G for this value is negative 33 kilojoules per mole, which means it's what? Spontaneous. So what we're going to try and do is we're going to try and calculate G under non-standard conditions. So I'm going to give you the pressure of the nitrogen, which is 1 atmosphere, so that's under standard conditions. The hydrogen is 3 atmospheres, and the ammonia is 0.5 atmospheres. Okay? So remember, you can work in expressions in one of two things. You can work expressions in terms of concentrations. You can work this in terms of pressures. Okay? Same format is products over reactants. Something gets squared. If there's a 2 in front of it, it gets cubed. Same rules apply. You can use pressure as opposed to concentration. So I want to calculate delta G. So that's going to be my delta G naught, which is negative 33 kilojoules per mole. And then I'm going to run out of room. I'm going to write this down here. Then I've got my R value, 8.314 joules per mole Kelvin. And we're going to run this at 289, standard temperature, which is 298. Now, and then we're going to have the natural log, but because of the fact we're dealing with delta G and not delta G naught, or delta G naught, we're going to deal with Q instead of K. But that Q value, based upon that reaction, is going to be the concentration of my NH3 squared divided by the concentration of my N2 and my hydrogen concentration squared. Now, that's if you're dealing with concentration. These are pressures. So since it's pressure, the only thing we do different is that we go, oh, that's the pressure of NH3 squared, and that's the pressure of the nitrogen, and that's the pressure of the H2 squared. It's the exact same format. The only difference is if you're talking about concentration, you put it in square brackets. If you're talking about pressure, you put uppercase P. Okay? That's the only difference. The exact same format. It's still products over reactants. Don't worry about it. Okay, now, so in this situation, we'll take the natural log. If you plug in these numbers, so I've got my ammonia, which is 0.5. That's going to get squared. And then I've got my nitrogen, which is 1. And then my hydrogen is 3, and that's going to get cubed. Okay? So, now, here's the trap. Here's the trap. I've got the delta G naught in kilojoules. This is in joules per mole Kelvin. And I promise you, this is what you're going to do wrong. You're going to write it. Yes, you will.
And we lie.
And you lie. You're going to write this down, and you're going to leave that as 33, and you're going to briskly type numbers into your calculator. And you're going to get an answer that's completely wrong. Because you're trying to add kilojoules to joules. Because you just write down the numbers without paying any attention to the units. I promise you, you're going to do this wrong. or you're going to forget to square or cube something on the other side. Okay? And you all sit there today and go, don't be silly. We won't make that mistake. Okay? So, what do you want to do? Do you want to roll the kilojoules into joules, or do you want to do the joules into kilojoules?
Joules to kilojoules.
Okay? So we're going to divide by 1,000, and we're going to get 0.008,314 kilojoules per mole Kelvin times 298 times all of that. So, if you really want to crunch the numbers, you can, but trust me, you get a negative number out of all of that. Okay? You can crunch the numbers later. So here's the point. You're going to get a negative number. So let's look at this. Mathematically, look at what's going to happen to that Q value. Okay? You got 0.5 base squared basically divided by 9. You have 0.5 divided by 9.
Wait, is that 3 cubed or
3 squared.
It should be.
Okay?
It should be.
Oh, it is cubed. 0.5 divided by 27. So here's the point. You're taking the log of a number less than 1, which is going to make it what?
Negative.
A negative value. So you're going to have a negative value here added to another negative value there. So is there any way in this situation delta G to be a positive value? No, because you're adding 2 negative numbers together. What would you want to do? And this is what you need to understand conceptually and mathematically. What would you want to do to that Q value? Because that's the only variable that you can change. Okay? That's it. That's the only number you can. What would you want to do in terms of the pressure of the NH3 and the N2 and the H2?
You need the reaction to go in the forward direction.
You'd actually, well, here's the story. You got this negative number here, right? So if you want to make delta G go positive, would Q have to be a really big number or a really small number? Q would have to be a really big number. So that way you're taking the log of a big number and adding that to that negative value, that delta G. Now, if that's the case, look at this conceptually. You'd make a whole bunch. You'd have a very, very high pressure of NH3. You'd have a very low pressure of your N2 and your 3H2. So imagine this. You're basically overloading the system with a whole bunch of product, and you have very, very little reactant. What's the system going to do? Go in the reverse direction, which means delta G would be a positive value, because then it would be non-spontaneous in the forward direction. So you can do this, okay, but you have to make, and this is what you need. You need to understand this mathematically, and you need to understand this conceptually. If I overloaded that system with NH3, Q becomes a big number. Mathematically, then I'm adding that to the negative 33, I would get a positive delta G. If in this situation where I have, if you look at this, I have very high pressures of my reactants. I have very low pressures on my product. So I have a lot of reactants and very little product. That's going to force that in the direction of making product. Okay? Go with this. Now, here's what this point, what you should be able to do. So we're going to keep the same reaction. So let me rewrite it so everybody's got this. Okay, so at this point, you should be able to, given this reaction, you should be able to calculate delta S, delta H, delta S of the surroundings, and delta S for the universe, and explain the correlation between all of the signs.
Wait, universe is just system plus surrounding?
Huh?
Universe is system plus surrounding?
That's one way that you can do it.
What, there's a second?
There is.
Okay.
You'll get the same answer. So, if you're going to find the delta S, I'll give you the answer at the end, just to save some time. So, if you look at this, you'd have to go to the book, and on the test on Friday, I'm going to give you a chart that has all the information that you're going to need, okay? So don't flip out and go, oh, Mr. Burkham, do we have to have these memorized? Yes, I'm going to expect you to memorize every thermodynamic bit of information on every possible element that I can know.
No way.
No, that's just stupid. So, to save you some time, so you're going to look at the NH3 and then you can subtract the N2 and the H2. If you do all that math, you get negative 198 joules per mole Kelvin. Does that fit with what we said should happen? Why?
4 to 2.
You started off with 4 moles of gaseous reactant. You ended up with 2 moles of gaseous product. That sign of delta S fits. Okay? Matches what we said was going to happen. If you do the same thing with the delta H, you get negative 92.38 kilojoules per mole. Why does that match?
So,
Temperature dependent.
Temperature dependent, because if we had done that, and let's say that we would have gotten positive 92.3, no bueno. The reaction would have never happened. We would never be able to produce ammonia. Okay? Literally, we wouldn't be able to produce it. If that's what you got, you would not be able to produce ammonia. If you had done that, and you had created a positive delta H. Okay? Like, there's no point. We can't win because it would never be spontaneous. Now, for the delta S of the surroundings, this equation is not on your equation sheet, but it's a handy little thing to know. That's negative delta H over temperature. Okay? So, in this situation, and here's the importance of this negative that's in front of this. So, you're talking about the delta S for the surroundings. So, what's happening to the system? What's that? It's going, that has a negative delta S, right? So what that means is that for to be a spontaneous reaction, a decrease in entropy in one thing has to be accompanied by an increase in the entropy in something else. Okay? So that's the significance of this negative delta H. So again, understand this. Yesterday, I didn't do it just because we would have run out of time. I could have had you all, for example, on that magnesium and hydrochloric acid reaction, I could have had you all calculate the value of Q, said, oh, okay, hey, here's the mass of the hydrochloric acid, which is basically like water. You would have known the change in temperature, the temperature would have gone up. So you would have said, oh, the temperature went up, it's an exothermic reaction. You could have calculated delta H. And it would have been a negative value because you could have taken the Q and divided it by the moles. You could have gotten delta H. You could have calculated it. But again, I did not give you the enthalpy probes because enthalpy probes don't exist. But you can determine delta H by measuring change in temperature in the quantities. Divided by the moles, there's your enthalpy term. Boom, there you go. So the reason that negative sign lurks out there is because this is basically going to be the negative of a negative. So that means that that's going to make the change in entropy of the surroundings be a positive value. Okay? So if you do the math on this, you get 310 joules per mole Kelvin. Okay? I'm just doing that to save you some hassle. So, but here's the bigger idea. Notice that that's a positive value, which should make sense because, number one, you have an exothermic reaction. Energy is being given off. What's that going to do to the surroundings? Oh, you've given Skittles to Timmy. Timmy's going to be bouncing off the walls, and the surroundings are going to have more entropy because of the fact that you've given off heat. So the delta S for the surroundings is dependent upon what's going to happen with the delta H. Oh, he's given off. Timmy gets Skittles. Hey, let's go bouncing off the wall. Okay. Now, to get delta S of the universe, there's two ways that you can do this. One is that you can take delta S for the surroundings and add that to delta S for the system. Okay, that's option number one. Now, here's the story. First law of thermodynamics says that any reaction that is spontaneous does what to the entropy of the universe?
Increases.
Increases it. So, this is the only way that can happen. This is where it has to be consistent. So, if you look at what's going to happen, and I'll just save you some time. So, in this situation, you would have negative 198 joules per mole, and then you add that to the number that we just found, the 310 joules per mole, and you get 112 joules per mole Kelvin. Okay? You add the numbers together, you get a positive value. That makes sense. Oh, okay, because we said, if you go way back up to this idea, that delta G naught was a negative value. Oh, this fits with that idea that says, oh, we're going to increase the entropy of the universe. Cool. Now, the other way that you can get delta S from the universe is negative delta G naught divided by temperature. This is the other way that you can make it. Now, again, notice that there's this lurking negative sign in front of it. It has to be consistent. So if you have a negative delta G in and of itself, a negative delta G makes it spontaneous. But if you put a negative in the negative, that makes it then spontaneous because then you're going to increase the entropy of the universe. Okay? So if you do this, and you take that technically 33.4 kilojoules and you divide it by that temperature of 298 Kelvin, you get the exact same answer once you change that into joules. So there's two ways you can calculate delta S of the universe. Add the systems to the surroundings, take the negative delta G naught, divide that by temperature. There we go. Okay. Let me hand out your assignment.